everyone. Thanks you for the introduction. Indeed, my name is Carl Mensch. I work at the University of Antwerp, where I represent both the National Competence Center Belgium, which I will talk a bit about in a minute, and the Flemish Supercomputing Center, which has hubs across the different Flemish universities. Today, I want to talk about OpenFold, which was installed only a couple of weeks ago on our clusters in Ghent and at the VUB. So with the help of Kenneth and Sam, we installed it at those two sites already. And we tested out a few things suggested by PUXANO, for example. As I said before, I work for the National Competence Center, so I will start out by explaining a little bit how HPC, so high performance computing, is organized in Belgium. In Europe, a lot of money is being invested in supercomputing, building data centers and HPC centers. And along with that, also the European Union is investing a lot in a network of competences. So in each country, a national competence center is being created. So the past 2 years already, there was the first phase of this project, and now we're continuing this. And the goal is to have a dedicated network of people with all the competences necessary to run HPC infrastructures. Also, along with that, an important part is providing training for through the National Competence Center, and also part of what I'm doing, for example, is to foster industrial uptake of high-performance computing. The National Competence Center in Belgium, as you can see on the right-hand side, consists mainly of the Flemish and the Wallonian universities, which host the HPC infrastructure in Belgium. So in Flanders, we have the Flemish Supercomputing Center, and in the Walloon region, we have CC, which are our colleagues, and Senaido that operate the HPC centers there. In Flanders, we have 5 universities, and all of them are part of the VSC. So the VSC is a collaboration agreement between the different universities. And in 4 out of the 5 universities, we have HPC infrastructure installed. The way high-performance computing is organized in Flanders and basically throughout Europe is you have 4 levels. The lowest one, the tier 3, is basically my laptop, your laptop, or a workstation you have in your department or in your group. And then beyond that, you have the tier 2 supercomputing clusters, which are available at the different universities. As you can see at the bottom, so we have systems installed in Ghent, VUB, Antwerp, and also in Leuven. UHasselt collaborates with the KU Leuven infrastructure. And then for more demanding compute tasks, we have the tier 1 system. So currently we have the 3rd system installed in Ghent, which is called Hortense. And Hortense is basically now our most powerful supercomputer we have in Flanders. For even more demanding applications, you have the tier 0, which are basically the European level supercomputers, where also the VSC participates in. So for example, Belgium has a large share in the LUMI consortium. So LUMI is the supercomputer in Finland, is the 3rd most powerful supercomputer in the world, and Belgium has one of the biggest shares in the LUMI supercomputer. As I said before, we have the tier 2 systems installed at the different universities, which are primarily used by academic researchers. And we have the tier 1 system, which is also used by academic researchers, but it's also the go-to place for companies that can run computational workflows at our center. And that's organized as supercomputing as a service, where we have a cloud component, a data component, which is basically a data repository, and then the most important part, probably the compute part, where you can run your computations. Maybe already relevant for today, so I will not go into the details of these clusters, but for software such as OpenFold, obviously GPUs are very important. And nowadays we have, I think in almost all our clusters, also in Antwerp, we have powerful GPUs available. And also, for example, in the tier 1 cluster, Hortense, we have powerful A100 GPUs. And we see that these GPUs are becoming more important in our data centers. This is an infographic of Hortense, so I'm sharing that one, as I said before, because it's available both for academic researchers as well as for commercial use. We have a main partition, which is basically the worker nodes, where you have a lot of CPU power. Some of them have more memory, which is the large memory partition. And then, as I mentioned already before, and which will come out throughout the talk, is that the GPUs are obviously more and more important, and very important for AlphaFold and for OpenFold, obviously. Something that's important to consider already now is that it's a shared infrastructure, so storage is also shared. The software is based on shared systems. A software such as OpenFold is very I/O intensive, which means that if you use a shared storage, that impacts the performance of such software, obviously. And then something I will also come back to later is that you can access our clusters, obviously via an SSH client to a terminal connection. But now we also have, which is something, if you haven't, some of the users are here in the audience, I see. If you haven't used it yet, we have Open on Demand, which allows you to connect to our cluster just through a browser. So much easier, and also easier for example, to transfer data to our clusters. The tier 2 systems are available for academic researchers. They don't require projects to be submitted and so on. So they're basically readily available. For the tier 1, it's a little bit different in that sense that for academic research, it's a project-based system. So you need to apply for compute time through a project application, which is then evaluated by our tier 1 allocation board, and it also includes a technical evaluation. For industry, it's different in the sense that there is an exploratory phase in which a company can basically freely use our tier 1 infrastructure for a set amount of time and for a limited amount of resources. So there is limits to the amount of CPUs you can use for a set number of days, and the same holds for GPU. If a company would extend beyond that, they would basically just be invoiced per hour for the resources they consume. And then support, training, and basic support is included in that pricing. What we are talking about today, OpenFold, basically started a couple of years ago already, when CASP 14 came out, and something called AlphaFold, which you probably all know, really grabbed the headlines both in scientific news as well as in popular media. So when AlphaFold 2 won the competition, very big headlines came out, like the protein folding problem was solved, and it was soon picked up by all media and by all scientific journals and so on. Also, in our case, at the Flemish Supercomputing Center, and our colleagues across Europe noticed that because AlphaFold was getting such a lot of attention, we also got a lot of requests to install the software, people inquiring with us how they could run AlphaFold, for example. And that's why we set out to do a little bit more around this specific software than we normally do for the software we run on our systems, that we tried to create a community around AlphaFold and other AI-driven structural biology tools, let's say. And then we noticed that a lot of companies were interested in sharing ideas and best practices around AlphaFold and related technologies, as well as people from the universities and from our research centers. We started then by organizing some community days. So in the first community day, Kenneth presented his findings and Jasper's findings running AlphaFold on our systems. The training is available on YouTube, and it's a very interesting to have a look at if you're interested in running AlphaFold and running OpenFold. Same goes true for some of the VIB training material that is available. So after we did the first community meetup, there was at the VIB, Alexander and Jasper organized an introduction to basically these types of tools such as AlphaFold. And they also have a dedicated webpage which they created where you can easily track how such software should be used and how you can run it on our infrastructure. And then the last thing we did was at the end of last year, we organized a user day for the AlphaFold users where we had very interesting talks from Samir, Yanani, and Ida, which are all available on our YouTube channel. So for those who are interested, definitely worth a watch. As I know quite a lot of people in the audience here were also present that day. And we had very interesting discussions that day also in the afternoon breakout sessions we organized. Today we're talking about OpenFold. I will use some of the benchmarking we did for AlphaFold, which I mentioned, which are available on Kenneth's YouTube video, but basically it's about how you run AlphaFold or OpenFold. It's about these things. So the software runs in 3 parts. So first you do a multiple sequence alignment, followed by a prediction, and then a relaxation step where you basically optimize the geometry of the protein to a relaxed structure. Why is that relevant? So AlphaFold and OpenFold, they both have a lot of dependencies. They have a lot of Python dependencies which run to drive the script. And then for the MSA part, there is software such as Jackhammer, which runs in the background. It requires CPU, but it's very I/O intensive, which I mentioned before. And that's important if you run it on a system such as ours, which uses shared storage, because that will determine the performance of programs such as AlphaFold and OpenFold. The prediction part of AlphaFold is using TensorFlow. It's then obviously very important to have a powerful GPU, which we do have at the VSC. And then the last part is a minor part, so it's the relaxation part can be run on CPUs or GPUs, but it's often a minor part of the total workflow. OpenFold is very similar in that sense, since it's basically a PyTorch reproduction. So some of the things I will show are benchmarks we did for AlphaFold, but they make sense for both softwares, of course. Then quickly, let's not go into the details. For the installation of AlphaFold and OpenFold, there's basically two options. You can use a container to run it, which is very simple. It's very quick to do, and basically quite user-friendly. The downsides are that it's not optimized to performance for your own hardware, and also that if you use pre-built containers, there might be trust issues. So depending on where you get the pre-built container, you should take care where you get it from. Option 2 is obviously the one we do at our center, which is installing all the dependencies and the software from source. That's quite time consuming, but on clusters, obviously this is streamlined. In our case, it's using EasyBuild, which is software used to build such software on HPC clusters. It's developed at UAntwerp in the VSC. And because of that, it's easy to imagine that if it's installed from source, it's actually optimized to run on your own hardware. So it will have better performance than the container. That's shown here. So this was for a run for AlphaFold, but the same holds for OpenFold, is that if you run it in a container, which are in both pairs, the left-hand bar graph, you see that it's let's say about 10 to 20% slower than the easy build installation shown on the right-hand side. I mentioned this already before. Next, so we have installed the software. AlphaFold and OpenFold are available on our clusters. You have set up an account, either if as an academic or as an industrial user. And then the next step is to connect to our clusters. As I said before, there's two ways to do this. You can use an SSH client to connect to our clusters, so using a terminal basically to connect to our clusters. Or nowadays, very interesting in Leuven and at UGent, you can use Open on Demand, which allows you easier access through a web browser, basically. Once you have connected to our clusters, so I mentioned already to Wouter before, basically today was about doing a little bit of a demo, but we took into account that if I would have connection issues today, or if what actually ended up happening today is that the cluster would be down, I could still show you some things today. So that's why I'm doing this in PowerPoint and not showing it to you live as a demo. But basically, if you log into our cluster, depending on which cluster you get into, you see a screen like this. In Ghent, it looks like this. And then you can start setting up your job. So to set up jobs at our infrastructure, it's important to realize that we have three main locations, let's say. So three main locations to store your data. You have the home, the VSC home folder, the data, and the scratch. And that's important to realize because they have set limits for the amount of data you can store there, and also the purpose is different. So the VSC home and the VSC data is available across all our systems. So if you log into Ghent or in Antwerp or in Brussels, you will all have this data shared. The home directory is meant for very small things such as configuration files. The data is meant to store your data or sequences or basically the input you need to run your jobs. And then the thing I most commonly use is the VSC scratch, which is much faster to be used in your calculations. It often also has much more space available for you to set up your jobs. That's also because it's meant to be fast. It's also the only one that's available only locally. So if you set jobs up in the VSC scratch folders in Ghent, it will also only be there, and you will not be able to access them from the VOB cluster, for example. That's only for the home and the data folder the case. And then specifically for Tier 1 and for industrial customers, I also want to note that there is a separate VSC scratch. Since, as I said, the Tier 1 is operated on a project basis, there is a VSC scratch folder projects base where for your project or your company, you have your own VSC scratch available with a lot more space there. Then this might be slightly different depending on which cluster you're on. For example, in Antwerp, you have access to submit jobs to our different clusters out of one single login. In Ghent, you have to select which partition you need. So with using module swap, you can select the cluster. For OpenFold, you'd obviously need a GPU partition, so you would swap to the GPU partition before submitting your jobs. Then to run software such as OpenFold or AlphaFold or any other software you want to run at our center, you need to set up a job script. In Ghent, this is done using Torque, so which are the, see if I can point, which are these PBS flags you see in the beginning. Then you need to select and load the software you need. So in this case, we want to run, for example, OpenFold in a specific version. Then for OpenFold, as I said, it does an MSA. For that, you need databases. It's very important to check where those databases are located. This depends, again, on the cluster you're using. And then lastly, here you see, for those of you who have run OpenFold in the past already, you will recognize this. Here, these are the options which you use basically to run OpenFold. So if we go into a little bit more detail, you can select a few options here. Not all of them are mandatory. Some of them are optional. For example, the first one is basically your job name. The second one, which you can choose, it has no impact. It's just for you to keep track of your job once it's submitted. The second line you see here, that's more important because that's actually where you request the resources you need, whether you need a GPU, how many CPUs you need, and how many nodes you need. So this is typically on the tier 1 what you would use. The GPU nodes on the tier 1 have 4 GPUs per node. So each of the compute nodes there has 4 GPUs and 48 CPUs along with that. So if you would use 1 GPU, you would most probably use 12 cores along with that. Then the wall time here is set to 1 day, which for a lot of OpenFold calculations would be more than sufficient, depending on how many sequences you want to run or how long the sequences are. Then here, this is basically all the output and error that the job creates. You can decide yourself where to store these using these -O and -E flags. Then this one is only relevant for tier 1 because there you basically have to provide with your tier 1 project or with your company project. Otherwise, the job will not run. And then lastly, something that's often nice to do is to keep track of your job. You can set it to notify you via email once a job starts, when it ends, or when it's queuing. For example, you can ask to be notified via email. So this is, for example, something that's definitely optional, but it might be nice to use if you need to keep track of some urgent calculations. Something that's also relevant to mention here is that OpenFold runs the MSA, so the multiple sequence alignments, and that depends on the memory you need. So for some MSAs, you need more memory, or you run into memory issues, and then you can increase the memory by setting the -L memory flag according to your needs. I mentioned it already a couple of times, but part of OpenFold and of AlphaFold is very I/O intensive, so a lot of data needs to be read when you run OpenFold. So the location of the databases you need to have a look at is very important. And it also depends on which cluster you're using. So for example, the first line is where it's located on the tier 2 at the VUB. The second one is where the database you need to run OpenFold and AlphaFold is located at the tier 2 in Ghent. And the last one, so in this case, it's not commented, as you can see, it's where it's located on the tier 1 in Ghent. You can also see that it's using the read-only option here of the file system, again, to ensure that the I/O phase is much more, the performance is much better than when you would store the data, access the data in a different way. The importance of the location of your databases is shown here. So on the left-hand side, as I said before, we have the VSC data, which is slower data because it's mounted across all different of our clusters. So that's a slow file system. The middle one is run on our VSC Scratch, which, as I said, is a fast storage place. You can see the performance improves a lot. So you see the red part is the MSA part, the blue part is the prediction, and the green is the relaxation. So you clearly see the MSA part, which is so I/O intensive because it needs to read all these databases. It goes much faster if you use a fast file system for that. And if you want to improve that even further, on the tier 2 in Ghent, for example, they have SSD storage. Basically, you can improve that even further by using that storage. It's 2.2 terabytes or something. So I think in total it might be 2.5 or something like that of terabytes. So it is really important to see where you store it and how you access it in our case. And obviously, it's not possible for everyone to have that available on your own laptop, for example. So that's why we decided it makes sense to make it publicly available through our systems. And then the last part of the job script. So the job script basically asks for resources. You need a GPU, CPU, memory, and so on. You need to find the correct databases and set up a few other things. And then lastly, you can run the OpenFold script. So these are basically all OpenFold settings, which some of you might definitely know a lot more about than me. But what you need to do is, so you run for example, if you want to run the pre-trained OpenFold script, you need to supply it with a directory containing your protein sequences. So it can just contain one protein sequence, but it can obviously also run for multiple protein sequences supplied in FASTA files. Then this is the section, as I mentioned before, which is very important to use the correct data folder that depends on your cluster. Please use these and do not download the database yourself. There is a reason why we have downloaded that for you. It doesn't make sense if 10 or 20 users would all download these 2 to 3 terabytes themselves, because we have already done that for everyone. Then this folder is where it will store the outputs. There it's important to take into account if that already contains alignments, the MSA step will be skipped. So that's important. If you would run a job and it fails and would run it again, if that output already exists, it will skip the MSA part. So you need to make sure that if you have done the MSA part, that you include it here. If you haven't done it yet, make sure that that directory does not exist. Model device, we've only run it in this fashion, so because that's basically telling OpenFold to use the GPU. There is a CPU only available, but I have not tested that yet for OpenFold. I will show some of the performance of AlphaFold of that in a second. Then here you have all the binaries. So again, you don't need to install these yourself, like Jackhammer and so on. They are all installed as dependencies on our systems. And then since we run easy build to install software, you can see the EB, so the easy build directories where the binaries are located are given here. And then you need to specify how many CPUs you set. So I've used just basically 12 because that's what we have available. But take into account that this might impact some of the performance. So I have not tested the most optimal CPU settings because it might be different for some of the dependencies for Jackhammer or so on. It might depend on there might be a maximum number of cores to maximize the performance of the dependencies. Here at the bottom is another database you need to use, the OpenFold parameters. Again, take this into account that the location of this depends on the cluster, same as with the databases. Then we've said so far that GPUs are very important to run OpenFold or AlphaFold, and that's very clearly shown here. So take into account that the y-axis is the elapsed time in hours. So here you go up to 20 hours. In the case of the GPUs, that is set to 1.5 hours, the graph. And you see here that the blue part, so the prediction part, so the actual running of the neural network is taking up here between 10 and 15 hours on CPU only. And if you look at the GPU, so we have V100s on the tier 2 or A100s, you see performance of the GPU is less than an hour. So clearly showing how important it is to have powerful GPUs to run something as OpenFold or AlphaFold. Then maybe for the users of the tier 2 and the tier 1 in Ghent it's recommended to use Stork. So as we showed before, you use all these PBS flags to require resources. If you want to see what's running under the hood, because the actual research and job scheduler is Slurm, you can use a command. You can submit a job with qsub and a dry run to have a look at what is actually running under the hood. So this is the way you it's recommended to ask for resources. But for people of you who are familiar with using a cluster that runs Slurm, you can have a look at the dry run and see what it's actually running. So for some of you, definitely the people who use multiple of our clusters in Antwerp and in Brussels, for example, we use Slurm. It might be worth to check using a dry run what it's actually doing under the hood. Once you've set up your job, you can submit it. In Ghent, that's using qsub. On Slurm clusters, that would be with sbatch. And then afterwards, you can monitor the queuing time and the runtime of your job using commands such as qstat and sq. So those are some very quick things to mention here. There's obviously many more things you can do to track your job and so on, but there's plenty of documentation on that on our website. Then for OpenFold, we run a set of proteins provided by Moises, of proteins of different lengths. So you see the shortest one was 148 amino acids in length. The longest one was over 3,000. We basically looked at the time to result. So how long it takes to run such a job on our tier 1 and tier 2 in Ghent. And I've compared that quickly with some of the things PUXANO did here at using their own workstation. So going from left to right, you go from the shortest sequence to the longest sequence. You already see something interesting. So you see both that the MSA part, so which is given here in red. The prediction and the green here are so short that you can't even see them anymore. But so the MSA part that is so I/O intensive, you see that it does not depend only on the sequence length. It also depends on the sequence itself. So that's interesting to note. For example, here, CFTR, which is about 1,500 residues versus PCNT, which is over 3,000. You see, even that's shorter than half of the length, it runs much longer, the MSA part. So the MSA doesn't merely depend on the sequence length. You see that for the prediction and relaxation, they are really minor parts for shorter sequences. It only becomes really important for longer sequences where you need a powerful GPU to run the prediction and also the relaxation part. Here you see the time elapsed up till 16 hours. So I've kept the same for the computations run by Moises at their workstation. So you see that the MSA part, given in red, takes less long than it did on our systems. Basically because, again, we have a shared file system, so that it doesn't mean because we're a supercomputer that everything goes faster on our system. So the shared file system is definitely worth noting that you're running your jobs on. And for the rest, you basically see the same trends. You see that the MSA time depends on the sequence itself and not on the sequence length. Then in this graph, we're only looking at the blue, so the prediction, and the green, the relaxation. So you see each pair of bar graphs gives the time it took to run it on the VSC, on the tier 1 in Ghent versus the workstation that was used here. And then you see for the blue part, because we have these A100 GPUs, which are very powerful, you see that runs much faster than using, for example, a GPU that has less power. So that's why you see that in all these cases, running OpenFold on our systems, because we have a powerful GPU and we have a lot of memory, it runs much faster on our system. So, as I said, we've only installed and have OpenFold available for a couple of weeks now in Ghent and in Brussels. So there's many more things we can have a look at, depending on your input, what's interesting to you as the users. Something that might be interesting is to try to improve the performance of the MSA. As I said, it uses dependencies such as jackhammer and others, which might be which might run more efficiently if we would look into how they are used. Also, we haven't looked yet at the MMSEC2 yet, which is available, but we haven't done that yet, and we should decrease the MSA times significantly. As I showed you, we basically use the standard way of running OpenFold. We have not looked at other configurations or other options that might be used, such as flash attention, to increase the performance. One thing we have looked at very recently, so the day before yesterday, my colleague at VUB did a test. They recently acquired GPU nodes which have almost 6 terabytes of local SSD storage. And then the performance difference can be shown here. If you would run OpenFold on human lysosime on just the general way using the shared file system, it would run for 1.5 hours. Using these local SSDs, it is reduced to 17 minutes. So it will be very interesting to see the performance of these nodes with a lot of local SSD storage on the other sequences we run as well. And then something I think is worth looking into is that the MSA part does not rely on a GPU, yet currently this OpenFold and AlphaFold only run on our GPU nodes, which is basically also, since the MSA part is taking up so much time where you don't need the GPU, you're basically taking hostage of a very expensive GPU. So this is something we definitely have to look into, whether we can run the MSA faster using MMSEC2, for example, or whether we can run it CPU only, which is currently not possible on our systems. And then other things we can definitely look at is we have not run OpenFold, the multiple version. I know OpenFold can also be trained, so it would be very interesting to hear from researchers whether they're interested in doing that and how we can help when you want to run something like that. And then lastly, I've commented on that in the beginning of my presentations. We have tried to create like a community around AlphaFold, OpenFold, and related technologies. So we are currently trying to set up what we're going to do with the community for this year. So if you have any ideas for that, feel free to let us know. I know some of the community members are here in the audience. We will probably organize another AI-driven structural biology day at the end of the year, but we're happy to have a look at ideas you have, things you want to run with us, or different software packages you want to compare, or the applications of different software packages and so on. Very keen to hear from you what you want to do with that. Then I think my slides can be shared afterwards. Happy to do so. I have collected here some useful resources. So obviously the OpenFold website. Then some of the benchmarks I showed today, you can download the sequences and the scripts that were used from our GitHub. Then Jasper, who is also here in the audience, did a very nice talk at the Easy Build user meeting last year about AlphaFold. And also Kenneth's talk, which I mentioned before, is available on YouTube, are well recommended to have a look at how you run AlphaFold and OpenFold. Both talks are very relevant in that regard. And then at the VIB, there's also this basically self-training available where you can have a look at how to run AlphaFold properly, but it's also really relevant to have a look at that to run OpenFold, since it's basically a PyTorch reproduction of AlphaFold. Then here, lastly, our websites, so of the VSC and the National Competence Center. There's a lot of documentations on our documentation website. So everything I mentioned today about how to submit jobs, all the scripts you need, all the commands you need to know, they are very well documented on the website, including the hardware we have and everything you need to run. The details on how to connect to the Open on Demand, for example, in Ghent and in Leuven, all that is available on that website. And then I would like to thank all of you for staying awake after lunch. I want to thank PUXANO and Wouter and Moises, obviously, for inviting me and setting up this day today. Definitely also very grateful to the VIB with Jasper and Alexander, who did a lot of work also on AlphaFold and on the community last year. I'm very grateful to the colleagues who worked together on getting the software properly installed. And our funding challenge, including the FWO, which is basically funding the VSC, and then Tim Jane, who took the lead in creating the community around these types of software. So thank you all for listening.